Assalamu alaikum dear students. Okay, last time we were discussing consequences of Syllow's theorems, and today we are going to prove 3 to 4 more consequences in this lecture. So one of them is, let H be a Sylow-p subgroup of a group G and N is normal in G. Okay, listen, H is a Sylow-p and N is normal in G. You have a Sylow-p subgroup and a normal subgroup. Then N intersection H is a Sylow-p subgroup of N. Firstly, you have to show that this intersection, you know that since H is a Sylow-p subgroup, so it is a p subgroup. And you know that intersection is a subgroup of a p subgroup, so it must be a p subgroup, right? So because you can say that N intersection H is in fact a p subgroup of N as well. So now you have to show that N intersection. So first thing is clear from the statement, right? So you have to show N intersection H is a Sylow-p subgroup of N, right? Again thing, H is a Sylow-p subgroup and N is a normal subgroup. Then you have to show that N intersection H is a Sylow-p subgroup of N. Look at here. This is your G and this is your H. Say it's a Sylow-p subgroup of G, and this one your N. Now this portion is N intersection H. Okay, we need to show that N intersection H is a Sylow-p subgroup of N. You know this portion, since H is a Sylow-p subgroup, so this is being a subgroup of a Sylow-p subgroup is a p subgroup. Yes, N intersection H is a p subgroup, and since it is a subgroup of capital N as well, so it is very much clear that N intersection H is a p subgroup of capital N as well, right? Now the remaining is to show that its index in N is relatively prime to p. If you can show this, then by definition N intersection H would be a Sylow-p subgroup of N. You know, we have given an alternative definition that if H is a Sylow-p subgroup in G, if index of H in G is prime to p, and equivalently you are saying that p power alpha divides the order of G, and no higher power of p is in fact dividing the order of G. Okay, so look at again that H be a Sylow-p subgroup of a group G and N is normal in G. Then you have to show that N intersection H is a Sylow-p subgroup of capital N as well. You can see the diagram. And Hn by N is a Sylow-p subgroup of G by N. Again you have to show that index of this in G by N is prime to p. Yes, so here you have to show that one thing is that index of N intersection H with P both are relatively prime. And secondly, you have to show that index of H N by N with P both are relatively prime. Okay, so this is another definition of a Sylow-p subgroup. You know very well, if p power alpha is the highest power of H, then of course index of H in G must be prime to p. So to show that N intersection H is a Sylow-p subgroup of capital N and Hn by capital N is a Sylow-p subgroup of G by N, you must have to show these two things. One is the index of N intersection H in N is prime to P, and secondly, index of Hn by N, this is the quotient group, with in capital G by N is also prime to P, right? Now we are going to prove, we want to give its formal proof. Okay. Let H be a Sylow-p subgroup of G with order of H is equal to P power alpha, and a normal subgroup of G. Okay, you also know a very clear result. If H is a Sylow-p subgroup of G, you know, this is a very easy result, you can prove this. If H is a Sylow-p subgroup of G and H is contained in another subgroup K of a group G, then H must be Sylow-p in K as well, right? Means that if H is a Sylow-p in G and H is contained in K, then H is a Sylow-p in K as well. This is our result. I already have proved in my previous lecture that if H is a Sylow-p subgroup of G and H is contained in K, then H must be a Sylow-p subgroup in K as well. Now look at here. Since H is a Sylow-p subgroup of G and H is contained in Hn, we know H is contained in Hn. Since H is contained in Hn and H Sylow-p subgroup of G, so H is a Sylow-p subgroup of Hn as well. Okay, I am using the same result. Since H is a Sylow-p subgroup of G and H is contained in Hn, so it is very much clear that H is a Sylow-p subgroup of Hn. What does it mean? This means that P power alpha divides order of Hn, but P power alpha plus 1 does not divide order of Hn. Okay. Now by Lagrange theorem, order of Hn is equal to order of H into index of H in Hn. Index of H in Hn, you know, this is order of Hn, this is equal to P power alpha, this is Hn H. Now you know, since P power alpha divides order of Hn, and p power alpha plus 1 does not divide order of Hn. So because Hn, index of H in Hn must be prime to p. So clearly index of H in Hn with p, for otherwise p divide index of H in Hn. So this imply index of Hn in H would be equal to some pt where t belongs to z, put in 1, you're getting Hn is equal to p power alpha into pt. So this imply which is equal to p power alpha plus 1 t where t belongs to z. So this imply p power alpha plus 1 would divide order of Hn, a contradiction. Okay, one thing we have established, since H is a Sylow-p subgroup of Hn, so that's why index of H in Hn must be prime to p, and p are relatively prime. If not, then p is a divisor of this. Then by definition of division, this must be equal to some pt. Putting here, so you are getting order of Hn is equal to p power alpha into pt, which is equal to p power alpha plus 1 into t, and this implies that p power alpha plus 1 divide order of Hn. But we have shown previously that if H is a Sylow-p subgroup in G, then H is a Sylow-p subgroup of Hn as well. So that's why p power alpha plus 1 does not divide the order of Hn. Okay, so that's why you are having a contradiction. Hence, order of Hn, index of H in Hn with p, both are relatively prime. Okay, so hence we have established one thing, index of H in Hn is prime to p. Yes, this is your number 1 star, you can say star 1. Okay, now we need to show that H, n intersection H is a Sylow-p subgroup of n as well. So we narrate the story that we have discussed. Since H is a Sylow-p subgroup, so n intersection H being a subgroup of H is a p subgroup, and since n intersection H is a p subgroup of H, so it is a p subgroup of n as well. Okay, since n intersection H is a subgroup of a p group H, so it is a p group itself. Hence, n intersection H is a p group in capital N as well, because we want to show that n intersection H is a Sylow-p subgroup in capital N. So first you need to show that n intersection H is in fact a P group in capital N. Yes, this is true here. Since H is a Sylow-p subgroup, so it is a P group, and since n intersection H is a subgroup of H, so it must be a P subgroup, and this is also a subgroup of capital N as well, so it must be a P subgroup in capital N as well. Now you need to show that. If you can show that the index of n intersection H in N is prime to P, then of course we can say that n intersection H is a Sylow-p subgroup in capital N as well. Okay. Next, by second isomorphism theorem. We see that Hn by capital N is isomorphic to H by n intersection H. Okay, this is very much clear. For this, you see that since n is normal in G and n is contained in Hn, so n must be normal in Hn as well. We have shown in group 3.1 that if n is normal in G and f n is a subgroup of a group, any group K of G, then n must be normal in K as well. So since n is normal in G and n is contained in Hn, where Hn is a subgroup of G and also containing n, where capital N is normal subgroup, so capital N must be normal in Hn. So that's why the structure is well defined. This means that this is a quotient group. Now, n intersection H. Since n is, we can show this. You need to show that n intersection H is normal in H. Okay. So first, you see that n intersection H is a subgroup of H. Yes, there is no ambiguity. So we show the normality that you take an element of n intersection H and take an element of capital H and show that H inverse is an element of this one. So we can show that this one is a normal subgroup in capital H. See how? Let x belong to n intersection H, so then x belong to n and x belong to H. Let H belong to capital H, and you take an element H from capital H and take an element x from n intersection H. You have to show that H inverse is an element of n intersection H. Okay, see. Now, if take x belong to H, then clearly H inverse belong to capital H. Yes, this is true. Since H is an element of capital H and you are taking the case when x belongs to capital H, so H inverse of course is an element of capital H since H is a subgroup, so this is trivial. Now secondly, you have to show that H inverse is also an element of capital N. Okay, so when you take x an element of capital N, now if x belongs to capital N, then again H inverse belong to capital N. Since n is normal in G, so your H belong to H is a subset of G, so this implies H belong to G as well. Look, this is also very simple. Now in this case, this H can be considered an element of capital G, because H is an element of capital H, and of course capital H is a subset of G. So this H is an element of G, and for all elements of G, since n is normal in G, so for all elements of G, in particular for all elements of capital H, Hx H inverse is an element of capital N, right? So see, this is an element of capital H, so this is also an element of capital N. So this means that this is an element of their intersection, of course, with H is element of H and X is an element of N intersection H. So this implies Hx H inverse belong to N intersection H, where X belong to capital H and H belong to capital H. So this implies N intersection H is normal in capital N, capital H, so this implies H by N intersection H is a quotient group, okay. This is so easy, you can easily show that N intersection H is normal in capital H. See, you take an element H from capital H and an element X belong to N intersection H. Now there are two cases. Since it is an element of intersections, of course X belong to N and X belong to H. Now if X belong to H, then this is of course trivially an element of capital H. Now if X belong to capital N, then Hx H inverse is also belong to N, since N is normal in G. So this condition is true for all elements of G and in particular for all elements of H as well. So that's why N intersection H is normal in capital H. So H by N intersection H is a factor group. So the structure is well defined. That's why you can use second fundamental theorem of isomorphism, or you can say homomorphism, right? Yes, we know the three well-known theorems. This one is the second one probably. Okay, this is the second isomorphism theorem. Okay. So from here, this means that this implies order of Hn by N is equal to H by N intersection H. You know, when two groups are isomorphic to each other, of course, we are giving two informations. One is their order is same, and the other is their structure is same, right? So that's why I can use that order of Hn by capital N is equal to order of H by N intersection H. Okay. So this implies, you know, the order of quotient group is in fact the order of G by order of H. So this is order of Hn by order of N. This is equal to order of H by order of N intersection H, and this further can be written as okay, because we want to move towards Hn by H, so that's why you can replace these two. So this implies order of Hn by order of H is equal to order of N by order of N intersection H. There should be the quality, right? And what is this? This is what is this? This implies this is in fact the index of Hn in H, index of H in Hn, and what is this? This is equal to index of N intersection H in N. Okay, now you know you are given that index of Hn in H is prime to P, so that's why being equal to index of N in intersection H in N is also prime to P. Backed by 1 star index of Hn, index of H in Hn with P, hence index of N intersection H with P is also equal to 1. Okay, we have established very easy that since both are equal, so index of N intersection H in N is prime to P. This means that N intersection H, being a P group, is also Sylow-p in capital N as well. This clearly shows that hence by definition, N intersection H is a Sylow-p subgroup of capital N. Right. Next, we need to show that Hn by N. What was the second answer? Second problem. Hn by N. Next, we need to show that Hn by N is a Sylow-p in G by N. Again, you need to show that the index of this in this must be prime to P. Right? Okay. Next, we need to show that. Next, we show that index of index in G by N, Hn by N with P is equal to 1. Okay, similarly we want to show that index of Hn by N, the index of this factor group in this factor group is prime to P. Then of course by definition this would be a Sylow-p subgroup of G by N, right? So let's prove this now. Now, you see index of G Hn by N. What is this? This is equal to, in fact, order of G by N, order of Hn by N, this one, and this is equal to order of G by N over order of Hn by N, like this, and this is equal to order of G by N over order of Hn, order of, by last theorem you have seen that Hn by N was isomorphic to H by, this was H, this was N by N intersection H, right? This was the theorem, Hn by N, or you can say that this is Hn by N, this is H by N intersection H. This means that order of Hn by N is equal to order of H by N intersection H. So look at here, you can replace order of Hn by N is equal to H by N intersection H. So this is equal to order of H by n intersection H, since this one the reason Hn by n is isomorphic H by n intersection H. That is H n by n order is equal to order of H by n intersection H. Right. So instead of writing this, you can write this. Now this becomes order of G by order of n over order of H by order of n intersection H. This further can be written as order of G by order of H into order of n intersection H by order of n, right? This further can be written as order of G by order of H whole divided by order of n by order of n intersection H. Okay, we can rearrange these things. This is equal to this one, and this one can be replaced by using the second fundamental theorem. Then use arrange orders with respect to your own convenience, because we want to see the index of G by H, so that's why I am taking order of G by H, order of H. Also I want to see the index of this, that's why I am using this. Okay, so this is equal to index of G in H divided by, or further you can write one step more, this is equal to order of G by H divided by order of n by n intersection H. This is in fact by Lagrange theorem, this is order of index of H in G divided by index of n in n intersection H. Okay, so we are at the step, right? And what was this? This was in fact index of G by n H n by n. Okay, we have established. Now if I can show that this is not divisible by prime number p, so this means that this index would be prime to p. So because Hn by n must be a Sylow-p subgroup of G by n. Now it's so easy. The rest of the problem is very easy. Since index of G in H with P are relatively prime, and index of n intersection H with P are relatively prime. Okay, you see this one, since H is a Sylow-p subgroup of H, so index of H in G is prime to P. Also you have shown that n intersection H is a Sylow-p subgroup of capital N. So because n intersection H is a Sylow-p subgroup in N, so I can claim that this one is also a prime to P. Hence, it is trivial that index of G by H by N intersection H with P or relatively prime. That is, this index is P2. So if it is not relatively prime, then of course P must divide this. Okay? So we will generate a contradiction. Otherwise, you see, P must be a divisor of this. Okay? So from here we are producing a contradiction. See, this is number 2 star. Of course, you have taken H as a Sylow-p subgroup of G, so index of H in G is prime to P, and you have shown that N intersection H is a Sylow-p subgroup of capital N. So because index of N intersection H in capital N is prime to P. And now I am claiming that their division is also prime to P. If it is not the case, then of course P is a divisor of this, right? For otherwise, P divides index of G by H by index of N intersection H in N. Of course, now this must be equal to some Pt, where T is an integer. So this implies index of G by H by index of N intersection H will be equal to Pt for some integer T. So this means that index of GH must be equal to Pt time index of N intersection H in N. Now look, you can treat this as an integer because index of N intersection H in N is an integer, right, by Lagrange theorem. It's a divisor of the order of the group capital N. So T is an integer, so the product of integer is an integer, right? This is equal to some P T dash, where T dash belongs to Z and T dash is equal to T into N intersection H, right? So this is equal to P dash, Pt dash, right? What does it mean? So this implies GH is equal to Pt dash, where T dash belongs to Z. So again, by definition of division, P will divide G of H. So this implies GH index of with P is equal to P, a contradiction. Or you can say this is not equal to 1. Of course, it is a P in fact, but you can say it's not equal to 1, a contradiction. A contradiction against 2 star. Hence our supposition is wrong, therefore that index with P must be relatively prime to P. This means that hence or relatively prime, consequently index of G by H, index of N intersection H in N, or you can say that N intersection N by N intersection H with P or relative prime. This ends by definition.